There. How are you doing?
Good, how are you?
Good. Just 1 second. Hello? Yeah, I heard Christy. That's all I could hear. Hello? 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 I got a student calling me here, Tinley, so something happened on the call, so I'll try to call her back here if I can. I don't know what happened there.
Well, I was talking to Caden the other day, and he said that Tuesday was the first day he was able to get in. All the other times he would put in, and he just said that it just sat there and wouldn't let him in.
What, Zoom?
Yeah.
Oh, okay. This is my actual cell phone. I didn't just call my cell phone just now. Yeah, this is Mr. Shelton. Okay. If I could stop you for just 1 second. So what's your last name? Oh, okay. K-R-I-S. Okay. Christy Taunt. Gotcha. Okay. Yes. I believe that was, it's actually the only graph is number 3, I believe, but yeah, I'll have to look it up here. I've just started another class right now online, so I need to do that. Can I call you back as soon as this is over with? Or okay, all right, thank you. Yeah. Okay. It's a different class. She can wait a few. Okay, we got Shayna has joined us. Click admit. We got that. Good afternoon, Shayna. Hopefully she can hear. Get that. Okay. All right, 1 more minute and then I start. Just to see if somebody else logs on. Note to self, call. Okay, call. Okay, well, this is being recorded, so I'll go ahead and start. If somebody logs in a bit late, they can go back and watch the recording. So what I'm going to do today, I had thought about giving a brief intro to chi-square statistics, but and I think I may still make a video on that, so you can look for it on Blackboard. That is 100% optional. Okay, there won't be an assignment for that, but I may give you a video introduction of it just because I think it's a really important statistic that people should be introduced to. So it's not required at all to watch that video, but if you're interested or have any interest in doing any more in statistics later, you may want to watch it. So I thought what I would do, though, because I was looking through the results on StatLab, and some people had a fair amount of trouble with some of these problems, and that's understandable. That StatCrunch, when you're not familiar with it, And these types of problems where you're doing hypothesis testing and confidence intervals, it's a lot to think about when the first time you see it. And then you throw in the virus and the change to everything online, and the fact that I guess a lot of people, I'm sure there are some people that just don't put out much effort, but I know a lot of people really do. And it's beyond their control. They have problems getting access to technology or good internet, et cetera, et cetera. So it's understandable that people were having some difficulty with these assignments, because had the virus not happened, you know, what I do in class is I work through all these assignments in class with everybody. So if you're there in the classroom, that goes a long way towards increasing your comfort level in working the problems for this class and understanding what's going on. And we have not had the ability to do that this semester. So what I decided, instead of spending any of your time on the chi-square on this regular meeting, I would just use this to talk more about what you're probably more interested in, and that's the final that's coming up. So, and I'm going to post this. So this video will be posted on Blackboard. You can go back and watch it again. And also on that note, so this morning I did a video with the other class, and it took forever. It was literally 3 hours, I think. Because my explanations are somewhat lengthy, and but at any rate, I did assignment 6 this morning, and I recorded that. So I'm going to post that this afternoon. That'll be on Blackboard. So when you're reviewing, and there's a lot of lost time in there because I'm going back and forth between screens a lot. And when you're doing this, you got to click share, unshare, reshare, and then sometimes you go back to the screen and it gives you a different screen anyway. So that ends up making it, you know, 3 times longer than it would be. But I worked through the entire problem set of assignment 6, so you can fast forward through there and hopefully see what you want to see. I did. Never fails that I think I've got something nailed down, and you end up making another mistake. So there was one problem on assignment 6, because what I've been telling everybody is always round. Okay, when you're going to calculate a number, to get the right answer in StatCrunch, where it wants a certain number of decimals, the rule that I gave everyone, which for the most part is true, okay? But bear me out on this. But what you do at each step, if you're doing some kind of calculation with it, say with a calculator, or you're using StatCrunch as a calculator, and you've got 2 or 3 steps in the process, write down each number to 4 decimal places. So you look at 5, round to 4. And then when you're finished, you look at the answer and see how many decimal places it wants. And then generally you're going to be right. And when you round your final answer to the number of decimals they want, you're going to be correct, okay? And so I had one mistake at the end of the session today. I thought it was funny because what I did was I calculated a number for, this is the last problem or next to the last problem. And then I wrote down, you know, what I had in the calculator, and I wrote it down to 4 digits. And then I looked, and the problem wanted 3, I think. So I rounded that to 3. Well, it was off by 1 digit in the last place. And so what the problem was, there's just one step in that calculation. So I rounded it twice, right? Because I was working quite a few problems, and I would just look at a result and I would write it down so I would be able to come back to it, right? So this had a lot of digits after the decimal, so I rounded to 4, wrote that down. Then I go back to the problem and read it, and it's just that one step. And then it says, okay, I want this answer in 3 decimal places. So I rounded that 4-digit number I had to 3 places, and the last digit ended up being wrong. Had I rounded the original number that I had in the calculator to 3 decimal places, it would have been correct. So I was laughing because I've been telling everybody now, always look at 5, round to 4. And then here I did that in the last problem, and that problem was wrong. But actually, it wasn't wrong. The problem was it was just a one-step calculation, and I actually rounded it twice, right? Because I rounded it when I wrote it down to 4 digits. And then when I read the problem again to see what they wanted, they just wanted that. Well, then I rounded it again. So that rule I gave you does work. But if you only have one step, you know, look at the whole number and just round that whole number down to the number of digits they want if it's just one step. But if you're doing multiple steps in a calculation, it's okay to write each number down to 4 decimal places. Look at 5, round to 4, do your calculation, and you'll be correct. So I just thought that was amusing that that rule kind of got messed up on me there at the end. But that will get you the right answer. Okay, so as far as reviewing for your final, let's see. It looks like we got another student joining here. I have to click admit. There, okay. Howdy, Lowry. Okay. So we're reviewing what's going to be on the final today. So go back and look at your stuff from earlier in the semester, okay? Like questions like, you know, how many variables? They'll show you a table, for example, and they'll say how many variables are being displayed here. So that one is pretty basic. I think you can handle that okay. Know that in statistics, which we've said many times, there's always this statistics. What you're doing is you're getting a sample, and you're wanting to make some statement or some estimate about a bigger population. Okay. Based on your sample results. So in statistics, you always have kind of 2 values you're concerned with. You have the population, which is the big picture, the big population, and then you have your sample, and your sample number is a statistic, and then you're going to make an inference about the bigger picture, which is the population, the general population, based on your sample. So that's what you're always doing. And these symbols that we use to represent different entities, for example, mean, when you talk about the mean of something, which is just the arithmetic average of something. Of course, for population, the big picture, what the value of the mean is for the whole population, which is what you don't know, it's what you're trying to estimate, that's mu. Lowercase Greek character, it looks like a U. I think you guys can click on this and enlarge it, that portion of your screen, but that's mu, so that's a population mean. And then, you know, X bar is a sample mean, right? So the big picture is always the population, and we get samples and we're trying to estimate things in the population. That's what we're doing. So when you have proportions, and it's unfortunate that this letter P gets used a lot because you can confuse it. Sometimes you say, is that proportion? Is it probability? Is it p-value, right? So, but when you're talking about proportions, P is the population. It's the big picture, population proportion. And then we know that P hat is the sample. proportion. So we get a sample p hat and we make an estimate about the value of p, right? So the population values are called parameters, right? And the sample values are statistics. Okay. I think everybody knows that. I'm just making sure. Okay, so in your review, take a look at histograms. And what do I mean by that? Well, there'll be several problems where they'll just give you a picture that'll show you a distribution. It'll show you a histogram, right? And maybe the question will be, what do you think this is a histogram of? And here's an example. Just by looking at the pattern of the histogram, you can understand something about a bigger picture, right? For example, it's this kind of shape here. You might talk about, for example, if I said, if I ask you, is this a histogram of, say, the average weight of American men between ages 30 and 60? You would look at this picture and think, well, perhaps not. You're not really sure with just that information, but you think, it looks kind of odd that you've got a lot of people with low weights and lower, or not a lot, but you have a lot of occurrences of low values, but you have a very high frequency of these three high weights. What I'm trying to get at here is that if you were modeling a big population of something, you're more apt to get something that looks more symmetrical and unimodal, right? This looks more like the shape you would have for a distribution of weights of, say, people or of men, right? You'd have a lot of people that would have a value around here and a smaller number that are quite a bit less than that and a smaller number that are quite a bit more. This would be the kind of thing you might look at and say, you know, what kind of population might have a distribution like this? And you could think, well, what an example might be, say, grades on an easy exam, right? If you had a really easy test, you would expect, so this would be grades here, and you put that on a numerical scale, like say, a 4.0 is an A, a 3 is a B, that kind of thing, right? So if you look at this, but your question might be, look at these two pictures and tell me which one is a distribution for weights of people. And you could look at these and say, well, people aren't distributed this way. You don't have a whole lot of really heavy people, and then it just tapers down like this. But grades on an easy exam, this looks like it might make sense, right? It means you have a lot of high grades, and then you got other values in here too, but you have a whole lot of high grades. So that's a lot of rigmarole, but what I'm just telling you is there's a couple problems where there'll just be a couple of shapes of distributions. So understand that what you're looking at when you're looking at a histogram is some scale that increases in value from left to right, whether it's grades or weights, and then this is frequency, of course, or counts, right? And if you just think about the picture and what the question is, you'll be able to match up. It'll make sense to you just from looking at a shape. So just go back through and look at some histogram shapes maybe in your book and what they represent, and you'll understand. Something that's important to know. Okay, remember we had measures of center for distribution. So there's different kinds of distributions, right? And they all do a measure of center. And we said we used the mean and the standard, well, the mean when the distribution was what? Unimodal and symmetric, right? Or it's like a single hump shape, right? And you'll recall, what did we use when the distribution was not unimodal and symmetric? What's a better measure of center? So I'll say not unimodal and symmetric. So you got some other distribution here. So what's a measure of center here, right? And of course, what we said in class was that's when you want to use the median, right? It gives you a more accurate idea of where this data is located. And when you say where it's located, you're talking about where it's centered on this horizontal scale, okay? If you just give somebody one number that represents where this is centered, the mean is not a great number to use for this when it doesn't have this unimodal shape, okay? The median is a better representation of that number. So those are both measures of center, right? The mean, maybe I should print it, right? And median are measures of center, so not unimodal. And what's another way this might be worded, right? Not unimodal and symmetric. How about skewed? Remember that? So if you have a skewed distribution, and you want to say, where's the center of this distribution? The mean is a poor choice for that. You want to use the median, right? So that's a measure of center. So these summary statistics, you got a measure of center and you have a measure of spread, right? Measure of spread. And for the unimodal symmetric, the thing that we're looking at most of the time with all of our hypothesis tests and confidence intervals, and that's because we use the central limit theorem. The central limit theorem applies to the normal curve. But what we use there as the measure of spread is standard deviation, right? So when you have this unimodal symmetric distribution, if you just give somebody two numbers, you give them the mean value and you give them the standard deviation, you've told them a lot about this. They know a lot about this from knowing these two numbers. This standard deviation would be the character sigma, right? Lowercase Greek sigma. So these are population parameters in terms of your sample, right? The sample would be X bar and S. right? This standard deviation of your sample and sample mean. Okay, so if it's unimodal and symmetric, we use standard deviation as the measure of spread. If it's not unimodal and symmetric, not and what's something that's not unimodal and symmetric? Skewed. Skewed is not unimodal and symmetric, right? So if something is skewed, what do you use for its measure of spread? You don't want to use standard deviation, right? You want to use spread, use IQR, right? Which is the interquartile range. Okay, and that could be, it can be for any shape that's not this single hump shape distribution. Okay, if you don't have this single hump that's kind of symmetrical or approximately this, and you're going to give somebody summary statistics on that distribution, you would give them median as the measure of center. So median measures where the center is, right? And the IQR measures spread. Another word for spread is variation, right? So know that. And you remember that the IQR is equal to the third quartile minus the first quartile, right? And another way of saying that same thing is the 75th percentile minus the 25th percentile. That's the IQR, interquartile range, interquartile range. Okay. Yeah, review your box plots, right? Review box plots. So if they give you well, so you may be given a box plot and asked to interpret it, right? So the interquartile range is what? It's just this distance. It's the in the case of vertical box plots, it's the height of the box, right? Because we know the boxes are from the third quartile to the first quartile, and then the line that's drawn inside the box is the median. And then the bottom number is the minimum value in the data set, and the top number is the max. So it's your 5-number summary, right? The min, the first quartile, the second quartile, which is the median, the third, and the max. Okay. But from looking at these, you can see in this sample, you'd say, well, which one of these has the most variation? Well, it would be this one, right? Because IQR measures spread of the data. And so that would be the tallest box. Okay, anyway, just take a quick review about, you don't have to spend a lot of time on it, but just make sure you understand box plots. Okay, correlation, right? You'll be given scatter plots, maybe 3 scatter plots. And you might be given a range of numbers and say match up, you know, A, B, and C with the correlation numbers here, 1, 2, 3. They'll have, you know, some numbers here. Which correlation goes with which one? So remember, correlation means it's a lack of spread, among other things, right? So this would be a high correlation. There's not much variance or variability in these data points here, right? About some line. So there's a trend line. There's a little more variability here, and there's a lot of variability here, right? So these are all X and Y axes. And you know, this would be, your correlation number would be positive here because the slope is positive. This correlation, if you were going to draw a trend line through it, it would be kind of like that, right? And so that's a negative correlation. As X increases, so if you go this way, what happens to the Y values? Well, they're coming down, right? So, you know, this is a negative correlation. This is positive. And so review correlation. Let's pull up, just so everybody will remember that a little bit here. Let's pull up my stat lab, and I'll reshare this screen with you. So if we're going to do a regression, I'm going to put some data in here. I'm just going to make some up, okay? Maybe I'll change this one to 56. All right, I just made some data up there, but let's do a correlation here of these two variables, okay? And we can go up here. I'll call this X, and I'll call this Y. All right, so if we want to do a regression of that, well, for one thing, we can do a scatter plot very quickly, right? If we want a scatter plot of this data to look at it, we can just say graph, and here's scatter plot right here. And it says select the X variable, okay? So X is kind of your independent or your input variable. So we would tell it this first column. I guess you got to click in here. And it says select the Y variable. So let's tell it Y is the second column. Okay, and that's all we need for this plot, I believe. And there, I told it to plot it. So here's a scatter plot. So you could see we've kind of got a trend here in this data, right? So this is going to be a positive correlation. As X increases, Y increases, okay? And the regression, somebody's asking, do you have to have formulas on hand? You can have notes on the test, okay? So yeah, I would write out your formulas for standard error, right? You've got one for the means, it's S over the square root of N, and you have standard error for proportions, which is square root of P times 1 minus P over N. You've seen that quite a few times. That's, I'm just trying to think on formulas. But it's okay to have notes, all right? So yes, you can write, you won't need a lot of formulas. It's a good idea to have those two. But let's do a regression on this data, so just so you remember how to do that, okay? So let's go stat, and it says regression, okay? And we're always doing the simple linear in this class. And once again, we have to tell it what's what here. So we're going to say the first column is going to be our x variable. The second column is going to be y. Okay, and that's all I think that's, I don't know. Yeah, that's all I need. What happened? I don't know why that's got a check mark on it there and that doesn't. What's going on there? There. Okay, let's say compute. And let's look at what we have here. So remember, here's your correlation. It gives that to you right here. You don't have to, you can get this out of a calculator also, okay? I do recommend, if you have Safari, I would download Chrome onto your computer. There's problems when you're trying to load StatCrunch from Safari sometimes. It's those pop-up blockers, like the version of Safari I have, I cannot turn those off. And so StatCrunch doesn't work right. But I had Safari, it's this computer I'm on now, and I downloaded Chrome, and it seems to work really well on here. So, and Firefox will work. Just, you can go in Firefox and disable pop-ups, but I was not able to do that. And I have, it's either 12 or 13, my version of Safari, and I couldn't turn the pop-ups off. Okay. So, but on this regression here's our regression equation, right? And so this second number is the slope, 1.9444, and this first number is the intercept value, 46.889. And this is the equation of the best fit line through here, okay? And let's review what these coefficients mean, okay? This intercept value is the value that y becomes when x is 0, okay? So if x is 0, 1.94 times 0, because that's what this means, this number times whatever your x value is. So if x is 0, y is just this intercept number, all right? And then the other number, 1.944, there are questions about that say, so what this means is for every unit of increase in x, every time x goes up by 1 unit. Now, when I say unit, I'm talking about whatever x is measured in, okay? So if x is measured in thousands of miles, okay, this is a number 2, 3, 4, but it stands for thousands of miles. Whenever this goes up by 1 unit, so 1 unit there would be, if this were thousands of miles, and we went from 2 to 3, from 2,000 miles to 3,000 miles, that's just an increase of 1, right? If x is in thousands of miles. So x, the value of x would be going from 2 to 3. If we went from 2,000 miles to 3,000 miles, x just changed from 2 to 3. So but whatever the problem is, for every unit increase in x, and by unit, just look and see what x is measured in. Whatever it's measured in, those are the units. Okay, so if it's measured in individual miles, then that's easier to think about, right? If you go from 4 to 5, you've gone up 1 unit, you've gone up 1 mile. But x could be measured in thousands of miles. So an increase of 1 unit is an increase of 1,000 miles, right? From 2 to 3, if x is measured in thousands of miles, is an increase of 1,000 miles. But that's 1 unit, right? And so this number says for every single unit increase here, y increases by the amount of this slope. So if this were thousands of miles, if we went from 2,000 miles to 3,000 miles for x, y is going to increase by 1.944 thousand, okay? Well, what, yeah, I said that incorrectly. Y is going to increase by this number, 1.944, in whatever units that y is in. So I have to be careful there because I don't have the actual problem in front of me. For every unit increase in x, y increases by this amount. That's what the slope tells you, okay? And so this is the equation. This is called the regression equation. Here's your correlation coefficient right here. And here's your r squared value, which is just, if you take this value and square it, you get this number, all right? And your correlation coefficient measures how much association there is between the two variables. And it's a number between -1 and +1, okay? So 1 or -1 would be very high correlation. 1 would be a high positive correlation, -1 would be very high negative correlation. I think that's all you need to know for correlation. And you get those same numbers, notice down here. They're written a little bigger, it might be easier to read, but it says intercept 46.88. See, that's your intercept from your equation up here. And it says slope. Here's the slope, 1.944, which is the number times x. So that does the regression for you, right? You just tell it which column has your x values, which column has your y values, and it calculates all this for you. Okay, let's go on here. Get out of that. So yeah, I'll give you a tip here on the final. When we're talking about correlation, one of your problems did involve flight times, okay, with airplanes and distances. So there is that problem, a problem very much like that on the final. So if you go find that problem in your homework, you can increase your comfort level with regression and correlation. Let's see. Okay, we want to talk about areas. My cat's jumping up on my lap here. We want to talk about areas of the normal curve. You know, I'm not sure. Could you guys see when I went into this? I'm not sure if you could see this screen or not. It says Caden needs in. Let me see if I can get over to this other menu. I don't see Caden. I just see Shayna and
He's already been let in.
okay. All I show is Tinley and Lowry here.
Yeah, Lowry's his last name.
That's his last name. Okay. Okay. Got it. Could you guys see that regression screen just now I was talking about?
No.
Okay. Yeah. It would help me if somebody would speak up if I'm going on and on about something and you can't see it, because that's not doing anybody any good, right? Let me go back. I'm going to do it again. So I guess I didn't hit the share at the right time. So let me see if I can pull that up again. StatCrunch. And okay, you can see that now, right?
Yes.
Okay, so I just made up some data and typed a couple. I got to get, I'll be right back. My cat is trying to take over here, so sorry. Okay, I won that one, at least so far. So in StatCrunch, if you want to do a regression, you have your data here. You can, if it's just a few points, it's very quick to type them in here. You just put your X values in one column and Y values in another. Or you can, from the problem, you can click on the icon if it's a larger data set, you know, and it'll load it into StatCrunch for you. So let's go stat and regression, simple linear. And we have to tell it which column has the X variable in it. So we select that. And which column has the Y variable. And that's all you need. And you say compute, and it gives you this quite a bit of output just for a couple of mouse clicks there. And so here's your regression equation. Y equals 46.88 plus 1.94x. That is the regression equation. That's the equation of the best fit line through your data. It gives you the correlation coefficient here, R, and also gives you R squared. And I've made this mistake. I've pulled this up and looked too fast, and you just see an R and write down a number and go. But notice you've got R's here twice, so get the right one. Correlation coefficient measures the amount of association between two variables, okay? R squared measures the amount of variability in the Y variable that is explained by the X variable. So they're related, but they're two different things. They are, R squared is the R value times itself. So if you take 0.8725 and square it, you'll get this value for R squared. No magic there. But what they mean are two different things, okay? And usually, I think on the final, it asks you about correlation of a plot. So that's where you can get it, okay? Notice it's a positive number. That means if X increases, Y will increase. Your intercept is the value that Y takes on when X is 0, okay? It's as simple as that. I was just trying to think of units here to put on these for you, but maybe you don't actually need those for this. So if you want to know what y is when x equals 0, you just look at your intercept number. That's the value of y. Okay, so the slope tells you that if x increases, this is where I was talking about going from, say, if x is measured in thousands of miles, then a 1 unit increase would actually be a 1,000-mile increase, okay? So if x goes from 2 to 3, that's a 1 unit increase. What that unit is 1,000 miles, but that's a 1 unit increase. So every unit increase in x, y increases by the amount of the slope, 1.944, in whatever units y is measured in, okay? You have the same information here. This is the intercept. It's in slightly larger print, so it's maybe easier to read. So you can just look here, the intercept, and here's the slope value. You don't need, for what we're doing, you don't need other information in this report. Okay. So that's a quick review of regression. You need to know about just generally areas under the normal curve, okay? So if you go here, stat, calculators, and normal, okay. So here's a normal curve calculator. We've talked about this. When this is 0 and this is 1, so we have a mean of 0 and a standard deviation of 1, that is known as the standard normal curve, okay? And so that means that this scale is actually z-scores. This is a z-scale, all right? But you need to be able to look at this curve, and given some values down here in x or in z, either one, you need to determine the probabilities of different events, okay? So the way this calculator works is, in here, since we have mean 0, standard deviation 1, this is actually a z-score on the horizontal scale. So this is the probability that z really is less than or equal to, and if you put a number in here, put any number you want, 2.3, compute. So what this calculator gives you is the probability that z is less than 2.3. It is less than positive 2.3 standard deviations away from the mean. So that's the red shaded area here. Okay, and this number on the right is the probability. This is a measure of this area, which is directly proportional to the probability that you'll get a value here, which is z equal 2.3 or something less than that. This is that probability. Okay, so if you were looking at this, there's a couple different ways you could go about it, but if you wanted to know, well, what's this probability of being in this tail, you could just take 1 minus this 0.989, and that would give you this probability, because we know the total probability is 1, right? You're under the curve somewhere. And so if you're not from here down under the curve, then the area that's remaining is equal to 1 minus this area, 0.989, okay? And these areas do correspond to probabilities. So this probability is equal to 1 minus 0.989. And you can know that you can do that for any arrangement of values here, right? So that's one way you could do it if you wanted to know what this probability was. The other way, here you can actually change this, right? Remember, you can change that to greater than. And now it directly calculated that probability. in this tail for you. So this is a probability that z is greater than this 2.3 is right here. Okay, now notice you've also got a between function here. You click between. Now you have the probability, and this is still z because we got a mean 0, standard deviation 1. That means that this is the standard normal curve. So this is +1 standard deviation, or z equals 1. This is z equals 2, z equals 3, right? Z equals -1. And so here we've got the probability that z is greater than or equal to -1 or less than or equal to +1 is 0.6826, that number there. And that's the empirical rule, right? This is the probability that we're within 1 standard deviation of the mean is about 68% of the time. It's 68.3, okay, is a little better approximation, or this whole number is an even better approximation than that. But so this is showing you the probability that you're within 1 standard deviation, that your z-score is between -1 standard deviation and +1. That probability is this number, 0.68268, etc. Okay, so no, if you're looking at this diagram, same thing. You could determine what this probability is, or what this probability is, or what both of these together are, just by doing some simple subtractions, right? Because we know the total area is 1, and area and probability are directly proportional. So this number is the area out of a total area of 1, 68.268% of it is between here. So that corresponds to a probability. So this area is a probability. This area is a probability. So these two tail areas together, the total of this wide area plus this wide area is going to be 1 minus this area, right? If we take the total and subtract this area from the total, what's left is the area that's represented by either being in here or being in here. So we could get either one of these values by subtracting this red area, which is 0.6826, from 1, right? And then this is always symmetrical. So we can always say that this area is the same size as this area. So if we know this total in the tails, we divide it by 2, and that's how much is in each one separately. Okay, so the empirical rule there, this shows that really nicely for you, because these are standard deviations. Let's put 2 standard deviations in to see it, okay? So the probability z is from -2 to +2, and we get 95.4%, okay? And that's, the empirical rule said that there's about a 95% chance you're within 2 standard deviations, and there you see it. The probability that we're within 2 is actually 95.4499 whatever percent, right? So again, no, you could get this area from doing subtractions, or this area, or both of them together, okay? Because the total area of the curve is 1. So if you subtract some portion of it from 1, then the balance is what you have left. And it is symmetrical, so these will always be the same value on either side, whatever value that is. So if there's about 5% of the area in these two combined, then each one has about 2.5% of the area, okay? And the thing that we see many times is, let's do that. This number z equals 1.96 comes up all the time when we're doing our 95% confidence intervals. Let's put that in here and see what changes. So notice at 2 standard deviations, we're 95.45 roughly is our probability, 0.9545 to 4 digits, right? That's within 2 standard deviations. But when we do all this business with 95% confidence intervals, we're not talking about a 95.4% confidence interval. We're talking about a 95.0% confidence interval, right? So let's put 1.96 in here and minus 1.96. And look what happens. And this is a very slight approximation error here, but you can see we've got 3 zeros after this. Okay, and that's because this number is rounded also. This number would be very slightly different than 196. But they're just using 2 digits. That's why we have this little bit of residual error here. But this is our 95% confidence interval. It turns out that Z is 1.96. So the probability that a random sample from a normal distribution will be within, will be greater than negative 1.96 Z or less than positive 1.96 Z. That probability is 0.95. Okay, so here is the case where we talk about that alpha a lot. Alpha equals 0.05, so that 0.05 is this tail plus this tail area. So each tail has 0.025 area in it, right, when you're doing a 2-tail test. And here you can get different confidence intervals, right? We can use this in either direction. Here I put in these Z's that I already knew to show you what the probability comes out to be, but you can go the other direction, right? You can enter a probability. So if I want to do something at an 80% confidence level, I can put 80 in here, and it tells me what the Z value for the 80% confidence level is, right? It's 1.2816, and it's symmetric, so there's always one on the opposite side of the mean that has a negative sign in front of it. So this is a probability that Z is greater than negative 1.28 and less than positive 1.28. That probability is 0.80. So this is the Z star you would use if you were doing an 80% confidence level, right? And sometimes a problem may ask you for a 90% confidence level. There's your Z star for 90% right there, okay? And you put whatever confidence number, you'll notice what's happening there is your Z star, your critical Z value, is only a function of what your confidence level is. That determines where you are, how many standard deviations away from the mean you are. That's what Z star is, right? And it has a different value for different probabilities, which are different confidence levels. So that's a nice feature of this calculator, that you can just plug in whatever confidence interval you want here, and it'll give you the Z star for that value. But you can go the opposite direction. If you know what some critical value for Z is, if you already know a Z star, you can put it in here. You put minus the number here and positive that same number, whatever. If you already know what Z star you want it to look at is, and it'll tell you what the probability or confidence level for that Z star is. So let's do that just for the heck of it. Let's put something else in here just to show you what happens. So let's say minus 2.5 to plus 2 Z equals 2.5. Compute, okay? So this would be our confidence level, 98.758. And this would be our Z star value, 2.5. So you can go either direction with this calculator. And remember, if you're doing confidence intervals or you're doing a hypothesis test where the alternative is not equal to means it's a 2-tailed test. And you always want to be here where you've selected this between thing. So you have a tail on both sides, okay? Because this thing can be in this mode, and that's where you're just, this is a one-tail test. If you're just testing if something is bigger than something, then you'll want to do a one-tail test. Or if you're just testing if something is smaller than something, you're doing a one-tail test, okay? Let me see, select that one, put a different value in there. Right, so, but just about all of our tests are either confidence intervals or the alternative hypothesis says it's not equal to, and if it says it's not equal to, you're going to do a between. Okay, but I just wanted to show you that there's one problem where it'll basically show you a slice, a red area, and it'll ask you about some probability, and it's some other probability in that area. And you get that just by subtraction, okay? So we know that this tail area plus this tail area over here, we get that from 1 minus what's in the red, because the whole thing is 1.0. So 1.0 minus the amount that's in the red gives us the amount not in the red, which is these two, and it's symmetrical, so they're half of each other. All right, I think I've touched on that. Let me go back to cameras. Let's see. Say stop share and highlight. There. Okay, so you'll have problems like this. You'll say, it'll say a distribution has, and it'll give you something like this, normal, and it'll have some number here, 88, 2 numbers here, okay? So this notation means that this is the mean value, okay? That's the population mean. This means that this is a normal distribution characterized by mean 88 and standard deviation, which is sigma of 15. Standard deviation. That's what this means, this notation. So if they give you, they said a distribution is characterized by this, that means it has a mean of 88, standard deviation of 15. Then they'll ask you a question like, what's the probability that X is greater than, and pick a number here, 92. That's the problem. What's the probability? So here's a distribution. This is 88 is the mean, right? Standard deviation is 15. So each one of these marks is 15 away, right? That's what Z-scores are. So they're asking you, so this one would be 103 here, and 15 would be 73 in X. All right, those are the values. But this is 0, 1, 2, 3. It's also Z-scores, right? -1, -2, -3. So to get the probability that a randomly drawn sample is greater than 92, okay, so here's your 92. They're asking you, what's this probability? That's what they're asking you in that question. That you get a sample, maybe I should say greater than or equal to, that you get, this is 92 here, okay? This point here, because this 88 is the mean. So how do we get that? Well, we have to know how many standard deviations above the mean 92 is, right? and then we can use our z-score calculator to get that. Or we could go directly to StatCrunch. Let's go back into StatCrunch again. Okay. And this was, we wanted to know the probability that X was greater than 92. So we're not doing a between thing. We're doing a test that we're exceeding some value. So we just want a one-tailed test, all right? So here we could just enter our mean value, right? It's 88. And we could just enter our standard deviation is 15. And the question was, it's a probability that X is greater than 92. So we change that to greater than, and we just put 92 there and we're done. We say compute and it gives it to us. Okay, so that solves this problem. Here's the probability that X is greater than 92. It's this red shaded area, and that's what this gives you. This calculator always gives you the probability in this box that is the red shaded area. So if the question said, what's the probability that we get something less than 92, you could just take 1 minus this number, and that would be your answer. That would be the probability that you're less than that. Or this tool, you can actually change this, right? So before I click on it, 1 minus, that's almost 0.4. So our answer is going to be almost 0.6, right? If I say the probability that we're less than 92. So we click on that, and there's the probability that we're less than 0.92. It's 0.6. So that tool will give that to you, right? Okay, I'm just thinking out loud here. Let's see. Oh, okay. So let's a question asks you what the 75th percentile of something is. Okay. Well, if we just put our mean and standard deviation in here and use this normal calculator, 75th percentile means that the probability, what's 75th percentile mean? It's the probability of getting that, of getting a certain value or less than that value is 0.75. That's what the 75th percentile means, right? Means the probability of getting that value or something less than that is 75%. And think of it in terms of exams. A bunch of people took an exam, right? And you say, well, Sally was in the 75th percentile. That means that 75% of the people either got what Sally got on her score, or they got less than that on it. So she's at or above 75% of the people. That's what it means when you say so-and-so is at the 92nd percentile on this exam. It means 92% of the people either got the score that they got, that person got, or they got something less than that. So it means that person is greater than or equal to 92% of the people. So, and this will calculate that for you. You say compute. So there's your 75th percentile. And this gives you the number in X, right? So if the mean were 88 and the standard deviation were 15, you say, what's the 75th percentile? You just put 0.75 is your probability, meaning 75% of all occurrences happen at this value or below that value. That's what percentile means. It happens at that or below that. So this has to be less than or equal to. Probability that X is less than or equal to this is 0.75. That's the 75th percentile in X. You can go 25th percentile, right? Whatever percentile, and now it gives you the new number. Here's the X value for the 25th percentile. So you just need to figure out what the mean value and standard deviation is, and you can use this calculator and get those real quickly. And then remember, the IQR was the 75th percentile minus the 25th percentile, right? So let me write that down here. So IQR equals the 75th, 75th percentile minus the 25th percentile. Okay, so we would take the 75th percentile, 0.75, and we get what's X there. So the 75th percentile is 98.12, okay? And then we get the 25th percentile. The 25th percentile is 77.88. So we would just subtract 77.8 from 98.1, and that distance is the IQR, which is a measure of spread for that distribution, and it's a measure in X, right? In X units. Okay, that's percentiles. Confidence intervals for proportions. Go back to confidence intervals. And I just did this. I did this a lot. I'm going to post the other video I made this morning. It's long, but a lot of it is me jumping back and forth between screens. So you can fast forward through there, see all the problems worked, right? That was assignment 6 for. So confidence intervals for proportion is always p hat plus or minus your margin of error. This is the general formula for any confidence interval, right? It could be, if it's for means, it's x bar plus or minus the margin of error, right? But we're doing proportions, so it's p hat, and the margin of error is always your critical statistic, which is z star, which we just saw how to get z star, right? And since it's a confidence interval, we're using between. And so again, we would put, now for this to be a z calculator, it says normal, but for this to be z scores, we had to put mean 0, standard deviation 1. Okay. And then z star just depends on the confidence level, right? So if I put 0.95 for a confidence level, my z star is going to be 1.96. And when I say compute, there it is. There's z star. Remember, this is a z calculator now, and here's z star, right? So the margin of error is z star times your standard error. And here we're talking about proportions. And so that's z, so p hat plus or minus z star times that. So if it's at 95%, which we just did, we know it's p hat plus or minus 1.96 times the standard error, right? And the standard error for proportions, square root of p times 1 minus p over n. And a lot of times we don't know what p is. P is the population proportion, but when we don't know what it is, we're allowed to use p hat as a substitute for it. So you can plug p hat in here, plug p hat in here, and you just do this arithmetic. You just take p hat times the quantity of 1 minus p hat, divide that by n, your sample size, take the square root of all that, that's your standard error, okay? So p hat is just a sample proportion. P hat is sample proportion. So you take the number of successes, and that's a relative term. It's whatever you're counting, you know. 58 people said yes out of 2014. Well, yes would be, we would consider that a success, whatever the thing is, but it's arbitrary, you know, what you call a success and a failure. It's just proportions. You can test anything that is dichotomous, that has two values. And one value, one category, one outcome, you call those successes, and then the others, you call them failures. But that's a very general term, and it's arbitrary, whether you call this a success or call that a success. But whatever the thing you're studying is, if you're taking a poll on people's opinion on gun control, you could say people that are in favor of it, you could call that a success. Or you could call, you know, if you're studying the people that are not in favor of it, you could call that a success. It's whatever you're studying, okay? Whatever the thing that you're studying, that it's the number of occurrences of those out of the total number, right? And so it's just a ratio. So number of successes divided by total. And so p hat is just the value of that fraction, okay? You go get your sample. How many yeses did we have? Well, how many total did we ask? And you just get that ratio, just divide it. And I had 43 people said yes out of 2018. So you do that division, that number, which will be, so p hat, right, is always going to live between 0 is going to be less than or equal to p hat, it's going to be less than or equal to 1, right? It's a proportion. So it's always going to be a value that's greater than 0 and less than 1, essentially. Okay, or it could be 1. If it's 0, it's probably not worth studying to begin with, right? Or if it's exactly 1, it's something you probably not studying it. But anyway, so 95% confidence interval, we know Z star is 1.96, and with proportions, we always use the Z statistic, right? With means, sometimes you use the Z statistic, sometimes you use T. And it mostly depends on the sample size. Sample less than 25, if your population's normal, you use T. But there's a special case if your population's not normal and you have a large sample, you can still use T. So the only time you use Z on means testing is when you have a normal population, means the distribution's normal for your big picture population, and you have a large sample size, n greater than or equal to 25. If both of those are true, you can use the Z statistic for means testing. If they're not both true, you're going to be doing a T statistic, or you're not going to do it at all. There's one case, if the population's not normal and you have a small sample, you can't do any tests on that, okay? But confidence interval for proportions, p hat plus or minus your critical Z, and we always use Z for proportions. You don't have to worry about T's on proportions, so remember that. Always Z test for proportions. If you can do a test at all, it's going to be a Z statistic, okay? And Z is always, for the 95% confidence interval, is always 1.96. And then you calculate what your standard error is. You just plug that in to the equation in your calculator, or get it from StatCrunch, right? And StatCrunch has got proportion statistics. This is in that other video from this morning, but remember, here's proportion stats, one sample. Now you got with data or with summary. Usually it'll be with summary. You don't have individual outcomes. You just got, okay, so many out of this many replied yes. Well, that's summary information. And you would put the number of successes. I'll just make up some numbers here. Say I had 43 said yes out of 2018 of something, right? And that's all I need. If I just want a confidence interval, then I don't have to worry about this hypothesis test, okay? If I just want a confidence interval. this doesn't matter. So just click confidence interval. And notice here, you can type in different values for a confidence interval, right? I could do a 99% interval. I could do a 95. I could do 90. I could do 80. Any value I want, you can put in here. Say compute, and it gives you a nice report. There is your confidence interval. Here's your lower limit, and here's your upper limit. And it gives you the standard error there, okay? All right, let's see, getting back over to this. Well, I'll just write standard error there. I'm not gonna calculate it again, but this gives you your confidence interval. So that'll be written as two numbers, you know, with a comma between them. And this is your lower limit, your upper limit. And the interpretation is that you are 95% confident that the population proportion is inside that interval, okay? When you calculate. So what you're doing when you calculate a confidence intervals, you're getting an estimate, right? You get a sample proportion, and you want to know how close is that sample proportion to the population proportion. What you really want to know is what is the population proportion, but all you have to look at is your sample. So you get the sample value, p hat, and then you calculate this interval based on your sample and the sample statistics. That gives you an interval, and if you're doing a 95% interval, you are 95% confident that the population mean is in the interval that you calculated, that it's in that interval, okay? All right, what else we got here? Probability that something is more than something away from something. I know that sounds like a whole lot of nonsense words there. So let me put some meat on those bones, okay? There's a problem on the final that says, what's the probability that some mean value is more than so many units away from the mean, okay? And here's how you would do that. You would go to calculators, normal, and if you're saying, what's the probability that something is more than so many units away from this mean value, kind of by definition, you're saying it could either be more than that by that many units, or it could be less than that by that many units, right? So you know you're doing a between function there. And so if we knew the mean value of something, I'll just make up a number here, and it had some standard deviation, and you say, what's the probability that I would be more than 5 units away from 65, right? What's the probability that I'm more than 5 units away from this value? Well, what you would do there is you would just say, what's the probability that X, what's 65 plus 5? 70. And 65 minus 5 is 60, right? Now this is the probability, and I say compute. So if the question was, what's the probability that I'll be more than 5 away from 65? Or the question would say, what's the probability that should be more than 5 away from something that has a mean value of 65 and a standard deviation of 2? That's the question. You say, well, what is 5 units away from there? That's what's the probability that I'm going to be greater than 70, or what's the probability I'm going to be less than 60, because I had to be greater than 70 to be more than 5 away from 65. I have to be less than 60 to be more than 5 away from this, right? But now this thing, which we've talked about, it's giving you the probability that you're inside here. So this isn't directly answering the question, but it gives you the answer in just one step, right? Because what you're asking is, what's the probability I'm going to be in one of these tails, right? If I'm more than 5 away from this mean, that means I'm going to be outside, I'm going to be above 70, or I'm going to be below 60. So I just put the limits in here, and this gives me the probability that I'll be inside those limits. And to get the probability that I'm outside, I would just take 1 minus this number. So, and these could be other numbers, right? The size doesn't matter. You could have something that's 40 something that has a mean value of 4,200 and the standard deviation is 38, right? What's the probability that I'll be more than 550 units away from this mean? Well, so add 550 to that, it'll be 4750, and subtract 550, and that would be 3650. Is that right? 3650 and 550. No. 4,200 minus 550. 550, 0, 5, 6. No, that is right. That is right. 10 carry 1. Okay, that's right. If the question is, what's the probability that I'm more than 550 units away from 4,200, I would enter it this way. This is going to give me the probability that I'm within 550 of being at 4,200, right? I'm within 4,200 plus or minus 550. That's all this calculator. It always gives you the probability that you're between something. But our question's asking, what's the probability that we're outside of that? So we just take 1 minus the probability that we're between it, right? And in this case, we got 1 because this is a very small standard deviation. And so to be 550 units away from this means we'd be way, way out here. And it's actually, this probability that we're between there is actually not 1, it's 0.999 something. It's a real high number, but there's some teeny, 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 tiny chance that we're way out here, right? So I didn't use good numbers. Let me change this. Instead of saying 38, let's make 380 the standard deviation. That's more realistic there, okay? So if this is the mean value of something we were measuring out here in society, and we knew it had this standard deviation, what's the probability that we would be more than 550 units away from 4,200? And you can do that, you know, for any number you want. What's the probability that we're more than 200 away from this? If we could randomly get a sample, what's the probability we'll be more than 200 away from this for a random sample? Just put it in there. So that's saying that the probability we'd be between 4,000 and 4,400 is, so the probability that we're within 200 of this is this number. The probability that we're outside of that, or we would be more than 200 away from this mean, would be 1 minus this, okay? Now the problem could say, what's the probability that we'll just be, that a random sample will be bigger than 700 units more than this? Okay, so let's go to this, just a single side calculator. And what's the probability that we're going to be bigger than some amount? So let's make it greater than. if we've got the mean and standard deviation in here, the probability that we're going to be more than, pick whatever number you want there. You know, what's the probability that we're going to be greater than 49.25? Okay, if the mean is 4,200 and this is a standard deviation, what's the probability that a random sample will be more than this amount? And it gives it to you right there. And this, in this case, is right. This probability that we're greater than that is this red shaded area, and we're done. It's right here. So this number in this box over here is always a probability. And those probabilities are always associated with how much area is in this different regions up here, okay? And actually, this is always showing you here, it's always showing you the red shaded area. So this probability is the probability of a random sample occurring here. Okay, I think I talked about that. P-value, I talked about that, and I put a link on yesterday, I think, and I talk about p-value in there. But what p-value is, and you can get that from this calculator, okay? If you know, let's change it to a standard normal curve. So that'll be 0 mean, standard deviation 1. Okay, so now we know, and let's change it to between. Because p-value, most of the time we're talking about two-tailed tests, okay? And we'll just clear this out. So here's what p-value is. If you get a sample, so let's do proportion. So we get a p-hat, right? Well, that p-hat has some z-score associated with it. And that's you were talking about formulas to recall that there's really not that many, but this one would be an important one. Okay. So it's to go back and forth. You can go from X bar and back and forth to, I'm going to put z-score here, okay? And also p-hat goes back and forth to z-score, right? Each X bar has a certain z-score associated with it. I don't know if you can see that there. Each X bar has a certain z-score associated with it. Each p-hat has a certain z-score associated with it, all right? And the formula is z, okay, for this X bars up here, z equals X bar minus mu, and sometimes you'll say mu sub naught, but this is either the population mean or the null hypothesis mean, which is the claimed mean, okay? It's basically the information you have about the mean of a population. So X bar minus the mean divided by the standard error. That's the z-score. And this is also known as the test statistic, right? Because it comes from the sample. It's Z star doesn't come from the sample. Z star just comes from your confidence level. That's the threshold that you're going to compare your sample against, right? And then p-hat back and forth to z. So z is very similar. So up here we took our sample value as X bar. Now we're talking proportions. So our sample value is p-hat minus, and up here we were talking about the mean because we were doing means testing. Here we're doing proportions testing. So this is the population proportion, right? Or it might be p naught if it's the null, but same thing. It's the population proportion or the claim population proportion divided by the standard error. And you know, we know that there's two different formulas for standard error depending on whether you're talking about means or you're talking about proportions, right? For mean, standard error is S over square root of n. For proportions, standard error is square root P 1 minus P over n. Okay, and notice I have this arrow going both ways because you can also take a z-score and get its x value. If you know the z-score, you can determine what value of x goes with that z-score, right? You just solve this backwards for x. So here you would say x bar equals z times the standard error, right, plus the mean. I know that's written kind of at an awkward angle there, but I drew this arrow to know you can go both directions. So if you have the z-score, if somebody says, oh, so-and-so hit 2 standard deviations above the mean, well, if you know what the mean is, and you know what the value of a standard deviation is, and here it would be standard errors, okay, then you can say what their actual x value was. You know, so you could, if the mean on an exam was 78 and so hit 2 standard deviations above the mean, okay, 2 standard deviations means their z-score is equal to 2. All right, so z is equal to 2. Well, what is their score? Okay, and you get that by just reversing this equation. You take the z, which was 2, times how big is the standard deviation. You have to know what the standard deviation is, and then you add that to the mean, right? And same thing down here. You can go, if you have z, you can go backwards and get p hat, right? Because then p hat would be z times the standard error plus the population proportion, right? So that's where you go back and forth between them. For each z, there's a p hat, and for each p hat, there's a z. Same thing up here. For each z, there's an x bar, and for each x bar, there's a z. That's what we're always doing, drawing this. You can always think of that as 2 scales, right? One of them is a z-score scale. -1, -2. And the other one is whatever x is in, you know, if this, whatever units you're measuring x in. If it's exam scores, this mean might be, you know, 88, 89, not whatever x is, right? And you can go back and forth. You can get an x value has a z value, or a z value has an x value, and it all just comes from where it's located on this curve, okay? What the value of this variable is. But mostly you go this direction. Most of the time you're figuring out what is z. If we know what p hat was, we get that from our sample. We want to know what's the z-score. And this, when you say z-score, I'm talking about this is the test statistic, right? Or if we go get a sample, we're doing means testing, we go get an x bar, we want to know what's its z-score. You plug it in this formula, but just know you can go backwards. You can go the other way, right? You can get x bar if you just know the z-score, you know the standard deviation, and you know the mean. You can get x bar. Or if you know the standard deviation and you know the population proportion, and you're given a z-score, that'll tell you what the sample proportion was. Okay. P-value, which I did talk about in the video yesterday. It's already on Blackboard, but p-value is if you take a z-score, let's say we got a sample and we knew its z-score was 2, well, I have to put minus on this side, minus 2.34. Okay, that's its, we knew it had a z-score of 2.34. And you say, what is its p-value? P-value is always it's the probability that you'll get a value at the value you got, which is 2.34, or something more extreme than that. And more extreme means further away from the mean. So it means you either get this value, what's the when you say the p-value, it's what's the probability of getting this or something greater than 2.34, but also the probability of getting minus 2.34 and getting something less than that. So p-value is the area in these tails. It's the chances of getting a more extreme value for z than what you did get. That's what it amounts to, okay? And so you can interpret that as a probability of getting the score that you did get, or something more extreme than that. And this calculator always shows you the red area, or the probability between these things. And the p-value is the probability outside of that. Okay, so the p-value would be 1 minus this. And half of it would be in this tail, and half of it would be in this tail. But the p-value is the probability of getting your value or something more extreme. More extreme meaning further away from the mean than what your sample was. So if it's further away, that means it's out here in the tail, of getting this or something further away out in the tail. So p-value is what is the probability in these tails. And that's the interpretation. And so when you're doing these hypothesis tests, you compare the p-value. I'll write that on a sheet here. You compare p-value with your significance level. If p-value is less than the significance level, you reject the null. Okay, if it's not, you don't. End of story. Okay, so real quick picture. So here's a two-tailed test. All right, so we get a z-star. Z-star, it's 1.96 if we're at 95% confidence, right? And here's negative z-star. So when we're doing these tests and talking about p-value, what we're basically talking about is if we get a sample that's past z-star or less than negative z-star, okay, its p-value is going to be less than this area. I'm saying, let's say your sample's right here, okay? If our sample is here, our p-value is just the value at that value. It's just the area under the curve from the value where you're. So this is our z score, or another word for that is z score is test statistic. Okay, so it comes from the sample, right? So our sample hit here. Here's z star. Z star is this big line. Okay, z in our z score, our z value for our test statistic, if it's greater than t star, the p value, which is this probability from our sample, out further than the tail. And since it's a two-tail test, you have to double that. You have to say it's this probability or the chances of getting something that was negative that amount also, okay? So this area is p-value. But the significance level is this whole area from your z star on out into the tail. So if the area from here out, okay, tail start here for significance level. Okay, so this, if your significance level is 0.05, it means all this area past this z star plus this area over here past the negative z star, okay? But it means this total area past your z star values is 0.05. That's what significance level is. It's the probability that you pass z star. Significance level is the probability that you exceed, I'll say exceed z star, okay? So if we have a 0.05 significance level, that's the probability in the tail past z star is 0.05. So if our sample hits out here past z star, its probability of getting at that sample or worse is called the p-value. And you can see, hopefully this is big enough. I'm going to make this, enlarge this, just to make sure it's big enough on your screen. Okay, so here, this big line is z star, okay? So the significance level is the area in the tail past z star, so this whole area plus the area on the other side, it would be past negative z star, so this whole area. So this area is the significance level, okay? You got 2.5% probability here and 2.5 here. If our sample hits higher than z star, so our test statistic z is greater than z star, and we're going to have less area at our sample value or more extreme than that, okay? And so in this test, we're compared, if the p-value is less than the significance level, we reject the null. So what's going on there is basically these tails are called the rejection region, okay? So if you're beyond z star, you're going to reject the null hypothesis. So you don't have to have p-value to do the test, but sometimes you're given p-value and you're not given a z-value. So that's why you need to understand what it means. If you know the z star and you know the z, you already know enough to do your test. If z is greater than positive z star, or if it's less than negative z star, then you reject, okay? End of story. But if you don't know the z's, if you only know the p-value, you can still do the test. You compare the p-value to the significance level. And the significance level is the probability that you're beyond your critical z, you're beyond z star. So it's the whole tail area past z star. And then your p-value is just the probability of getting a sample at the value you got or more extreme. So if you got a sample out here and your sample's past the z star, the p-value is going to be less than if this significance level was 0.5, if this z star is for the 95% confidence level, then this significance level, these two areas together, is 0.05, okay? And if that's the case, significance level is 0.05, if our sample lands out here past z star, its p-value is going to be less than 0.5 because it's a smaller area from the sample out than it is from Z star out. So if the p-value is less than significance level, reject the null. If it's not, you don't reject the null. And that's what's going on with p-value. So p-value means there's a if the p-value is a very small number, you're going to reject the null hypothesis. And what's very small? Something smaller than 0.05. So if you have a p-value bigger than 0.05, you're not going to reject. That means your sample's in here somewhere. If your p-value is greater than 0.05, then your sample fell inside of this Z star, okay, where Z star would be 1.96 for the 0.05 significance level. I know it seems like I'm pounding on that, but you need to understand what p-value is. I should draw it bigger. I just draw one side of it there just to make sure. So this is a two-tail test. So remember, we got a mirror image going on over here, but here's Z star. And Z star depends on whatever confidence level you're at, okay? And that defines where on this scale you are. So here's the mean. That's also Z equals 0, right? And so this is your significance level, okay? Significance level. And remember, you got the same thing over here on the other side, okay? You got a negative Z star. So the significance level is really, it's both of these. But this would be 2.5%, this is 2.5, if the significance level is 0.05. So if your sample hits anywhere past Z star, say your sample hits here, okay, so this is your test statistic, which is your sample Z, okay? Then the probability of getting that or something more extreme than that, meaning further away from the mean, is going to be less than this probability of getting Z star or more extreme. And the probability of getting Z star or more extreme is your significance level. Yeah, I could write it that way. The probability of getting Z star or more extreme, meaning further away from the mean, okay, is the significance level. So if our sample p-value, which is a probability of getting a sample value or something further out, if that exceeds the significance level, you reject. I did another video on this. That one might, but I was just trying to talk about it real fast there and ended up talking a long time. Questions?
It's just me.
Okay. You got
The
anything?
other two left.
Yeah. Anything you want to ask?
No, I'm good for right now.
Okay. Well, good deal. I'll get this uploaded. Good luck on the test. I did, I've been attempting to schedule this. It's with ProctorU, and they have to reply to me. I registered, I uploaded the test, but they have to reply and say, okay, now your students can sign up. So that's what we're waiting on. So sorry, we can't tell you sooner, but we're waiting on ProctorU to give us the green light now. And as soon as they tell me, I'll email you, okay?
Okay, so the test is on Tuesday, correct?
Well, you'll have 2 days. You should have 2 days you'll be able to schedule it. You can either take it Tuesday or Wednesday is the way I set it up. So there'll be like a list of times, and you should be able to go in there and pick which time you want. but I'll send you an email as soon as they respond to me.
Alrighty.
Okay. Well, good luck. And
Thank you.
if you have any questions, you know, over the weekend, just email me or call or something, and we'll talk about it. And I
Alrighty.
don't think it'll be too bad. I think it'll be okay. All right.
Okay. Thank you.
Have a good day.
You too.